And we are back. Dr. D from ACU here. Let's talk about circular motion. So, having just spent a long time discussing forces and accelerations and Newton's laws, there's a really nice, simple application that explains a lot of really cool stuff. So, I like this section a lot. So, to start off, let's imagine a car driving around a circle at a constant speed. So, here's the path of the car. Now, its velocity is always going to be tangent to the circle because that's the direction that I'm going at some point in time. If I have acceleration in the red direction, either forward or backwards, I'm going to be changing my speed. And I want to be at constant speed instead of speeding up or slowing down. However, if I turn in the blue directions, then I could be turning to the left or to the right. So to drive in a circle, what I need is to have always the force, the acceleration, pointing in the blue direction, always turning, never speeding up. So the punchline is, to drive in a circle, the acceleration must always be inwards towards the center. This gives us a cool Latin word, centripetal. Centripetal means center seeking, in the way that centrifugal means center fleeing. Now, you know the word fugitive, that's someone who's running away. We don't have an equivalent English word for pedal that I can think of off the top of my head. But remember, centripetal, center seeking, and centrifugal, center fleeing, are opposites. So to go in a circle, what I need is centripetal acceleration, something that's always going to make me have an acceleration pointing inwards towards the circle. So I start here. A few seconds later, my velocity is still tangent, but my acceleration is still pointing in, and I keep going, and I keep going. And as long as my acceleration points inwards, I'll keep going in a circle forever and ever. So how big is centripetal acceleration? Well, I can think about this. To go faster, my acceleration needs to get bigger as v increases. It also needs to get bigger as r decreases, right? I want to turn in a tighter circle. I need more centripetal acceleration. I know that acceleration's got to have units of meters per second squared. So I'm going to have some term where I've got a v in the numerator and an r in the denominator, and I need to change the exponents so I get the right units of meters per second squared to come out. And so I can think about this for a little bit and guess my equation for centripetal acceleration, v squared over r, has all the right features to it. Again, you don't need to memorize it, just units and a little common sense will get you there. This is a vector. So the magnitude is v squared over r, where v is the speed, r is the radius of my circle. The direction always points inwards towards the circle, because that's the direction that the velocity is changing. So from the last chapter that we discussed, this is chapter 4 in the textbook that I'm using this semester in class, we know that accelerations are caused by forces. That's what F equals ma means. So to have a centripetal acceleration, I need some sort of force that's always pointing inwards. And that's what we call a centripetal force. So F equals ma is still true. So mass times the acceleration from the last slide gives me an mv squared divided by r. Now the one thing that confuses people most on this section, and the one thing that I want to be really clear about, is centripetal force is not some kind of brand new force that we've never talked about before. It's not a new kind of force that exists. It is only the name given to any other force that happens to be pointing inwards to make an object go in a circle. Any kind of force can be a centripetal force. So all the forces we've discussed so far, gravity, friction, the normal force, tension, weight, any of those could be a centripetal force if they just always point inwards. So remember, centripetal force is not a new kind of force. It's just the name that we give to any inward pointing force. Now again, this formula is for the magnitude. The direction is always going to be towards the center. So my force is continually changing direction as I move. And that change in direction is what's causing me to always accelerate, causing me to always go in a circle. So today we're going to do 3 quick examples of centripetal force and see what we learn. So number 1, if I'm in a car going to take a turn and I'm on a flat, level surface, it turns out that it's the static frictional force from the tires that provides the centripetal acceleration. So I'm going to say that the static frictional force is my centripetal force in this situation. Now, why static? The car is moving, but remember, the car is moving in this direction. So things that are making me speed up or slow down with my tires, that's going to be kinetic friction with my tires hitting the street. But in this direction, left and right of my car, where my tires are hitting the road, this is now a static frictional force. So when I turn my wheels to the left, it's the static frictional force that makes me turn. We can calculate how fast we can go to make some kind of specific turn. So here's the way all the problems in this section work. I say my force needs to be equal to mv squared over r. So then for whatever force I have, I kind of plug in what I know about that. So this is the equation for any kind of centripetal force, and I'm saying now my centripetal force is static friction. So from last time, static friction equals mu times n, that's the fun equation. So I've got mu times my normal force is mv squared over r. Now for an object sitting on a flat level surface with no other vertical forces, the normal force is just mg. So my left side is now mu mg equals mv squared over r. Okay, let's cancel out the m's and clean this up. So for this case, let's solve for the velocity. How fast can I go to make a turn? Now if you remember, the frictional force, the static frictional force, can have any value from 0 to some maximum. And what I've calculated here is the maximum frictional force. So that maximum frictional force will give me the maximum velocity that I can make this turn. So take my equation here and solve it for v. And after some algebra, I get v equals the square root of mu times rg. So this equation could tell me what speed I could take this turn on and actually make it around the corner and not go crashing into a ditch. So we could actually use this in a lot of interesting situations. So 2 things. First off, remember that mu, our coefficient of friction, changes based on the conditions of the road and your tires. So when the road is dry, mu is large. When the road is wet or icy, mu is very small. So a turn you can take in dry conditions, you cannot take in wet conditions. There's also a really neat application of ice driving physics on this. So imagine my car is sliding on the ice. So we've lost control, we're going to crash, we're going to burn up and die. If my car is sliding, that means my velocity vector and my tires are now pointing in different directions. So I no longer have this static frictional force making me turn because I'm moving in all these components. So if my car starts to skid to the left, I'm inclined to try to turn to the right, but that's the absolute worst thing I can do. That makes things worse. What I do is I turn into the skid. I turn my tires pointing the same direction as my car's velocity. So when I do that, I regain the ability to use the static frictional force to make me turn. So physics can keep you alive. A second example of turning cars. So let's talk about now a banked turn where my road is tilted like it is for, say, professional race car driving. So we can go around these turns a lot faster. Now I could actually completely ignore friction, and if I wanted to, I could let the normal force be my centripetal force. Remember, any kind of force can be centripetal. So on our diagram, here's my car. Weight's going down. My normal force is normal, that is perpendicular to my surface. So this component of normal force, sine theta, I know it's sine because this is the x component of my normal force. It's opposite from my angle, so I'm going to use sine. Normal force sine theta always points inwards. So that thing can be my centripetal force. So okay, normal force sine theta equals mv squared over r. Now again, if I want to solve for the velocity, how fast can I take this, I got to solve for how big n is. And I can use it by looking at this vertical. I can say my normal force cosine theta equals mg, algebra, algebra, algebra. And what we can prove is that the velocity I can take this turn at is the square root of rg tan theta. Now before we had square root of rg times mu, here we got square root of rg tan theta. So given a steeper bank, I can take this turn faster. So now let's talk about the thing that you all really want to know. You just might not have known it at the time. Physics is going to teach you how to fly. I mean it. So I think Douglas Adams explained this the absolute best in The Hitchhiker's Guide. There is an art to flying, or rather a knack. Its knack lies in learning to throw yourself at the ground and miss. And clearly it's the second part, the missing, that presents the difficulties. But it's absolutely right. All I gotta do to keep flying is to throw myself at the earth, but just manage to miss the ground. So let's see how we can do that. So imagine that I have an Earth, but it has no atmosphere. If Earth has no atmosphere, we'd all be dead. But if we were still alive, we could do a really interesting experiment. Let's go stand on the highest place on Earth, say Mount Everest. This picture is probably not to scale very much. And if I were to throw a baseball horizontally, if I could throw it fast enough, that baseball would go all the way around the Earth and hit me in the back of the head. Now, my baseball isn't doing anything different than any other object we've been talking about since projectile motion or the last chapter. So the physics isn't different because of the velocity. If I personally use my arm to throw a baseball, it's going to go 20 feet and stop. A professional baseball player could maybe throw it a few hundred feet before it stops. But if I could launch this thing out of a cannon, it would follow the same physics. So what that means is when this baseball is in the air on my atmosphereless Earth, I guess I shouldn't even say in the air, when my baseball is in the vacuum going around Earth, there's only one force acting on it. That's gravity. And for objects that are only acting under gravity, we call that being in free fall. So as my baseball is going around, it is in perpetual free fall. The only difference is it's going so darn fast sideways that it misses the Earth and keeps free falling and keeps missing the Earth and keeps free falling. Douglas Adams was exactly right. To make something fly, all you got to do is throw yourself at the ground and miss. And you miss the ground by going ridiculously fast in the sideways direction. One cool example of free fall is from this satellite launched by the ESA called the LISA Pathfinder. What they did is they took two of these cubes, these 46 millimeter wide gold platinum cubes, and they're sitting now in perfect free fall around the Earth. A very sensitive system of lasers is going to watch for any cube to have the tiniest bit of motion. So any kind of strange force or something happening out in space, we can detect now with amazing precision for weird stuff like gravitational waves. Now that we can look for things like black hole merger and neutron star mergers, because astronomy is really cool. Okay, so if I'm in orbit, I'm in perpetual free fall. All I got to do is think about gravity always being my centripetal force. Gravity is always providing a centripetal acceleration. It's always my force pointing inwards. I'm moving sideways really fast. So just like we've done before, I say my force is mv squared over r. Now in this case I got to use Newton's law, not just the F equals mg. So I've got to do the big G m1 m2 over r squared. One of my masses now is the mass of the Earth. Then I got the m for the object that's going around it. Now just to recap, and I'll remind you of this again later on, this r needs to be the distance from the center of the Earth. So the r for my giant satellite here, that's roughly the size of North America, needs to be the radius of the Earth plus the distance above the Earth to get that right. But this equation now tells me all sorts of interesting things about how orbits actually work. So for example, let's take this equation and let's solve it for v. So I cancel out an m, I do some algebra, and what I get is v is the square root of g times mass of the Earth divided by this r. And again, that's this r radius of the Earth plus the height above the Earth. So I could tell you how fast it's got to orbit, it's got to be going to have an orbit of a certain r. And it turns out to be somewhere in the ballpark of 18,000 miles per hour to actually go around for some realistic value of r. Because again, you want to miss the ground, you got to be going fast. Now we can also use this equation to calculate a bunch of other interesting things. So here's my velocity from the last slide. Well, if I want to do one full orbit, I could also say my velocity is the distance that I travel, that is the circumference of my orbit, 2 pi r, divided by the time it takes to do one orbit. So I set these equations now equal to each other. So my velocity is my total distance divided by a time, where again, that r is the distance from the center of the Earth. So I could solve this for either r or t to do some interesting things. So suppose I take this equation, I solve it for t. Yeah, the algebra is a little gross, but what I get is the time to do one orbit of radius r in seconds. So I could figure out how long it's going to take a satellite to go around. Or I could take my equation, I could solve it instead for r. Now I get r is gmt squared over 4 pi to the 1/3 power. And this is going to be the distance of an orbit that gives me a specific time to go around. Now there's one really cool application of this. If I want my time to orbit to be exactly 1 day, so that is 24 hours in seconds, I could find the radius of that orbit that gives me that exact time. And so if I plug it in, I figure out that my r has got to be about 22,000 miles above the surface. But any satellite that's there is now in geosynchronous orbit. So it takes the Earth 24 hours to go around. It takes my satellite 24 hours to go around. So my satellite appears to be parked, stationary, above some fixed point above the Earth's surface. That's the backbone of our GPS system. My satellites know where they are, and they're not moving relative to Earth, so then I can figure out where I am. It's an amazing application of some really simple physics. So let me show you two other things that are completely unexpected that we can learn from looking at gravity and free fall and centripetal force. So here's a picture of our galaxy. The question is, if I look at this, I see it's got this classic bar in the middle with these spiral arms coming out. Just to help orient you, remember, you are here. So here I am in the spiral arm in some unfashionable part of the galaxy. The question is, what causes this shape? And the answer, well, it was theorized for a long time before we finally proved it, is straightforward, kind of awesome, kind of troubling. It's one giant black hole. The reason that our galaxy has the shape that it does is because in the center of this, there is one monstrously giant black hole that's attracting all this stuff to it. So for a long time, we've been watching stars near the center of our galaxy orbit. And what we see is they go around nothing. We see stars orbiting some black void in space. And by measuring the time that it takes them to orbit, I can calculate, that's right, the centripetal force. I calculate the centripetal force, I can calculate the mass of the object they're orbiting, and I can actually directly measure the black hole. Now, sometime, if this goes on long enough, who knows how much this black hole is going to eat, and if we're eventually going to land in there. Imagine what the night sky would look like when we get close. Now, one more surprise from astronomy. Let's now think about the stars that are going around in our galaxy. So our galaxy is very much rotating. Nothing had a zero amount of rotation or angular momentum, like we'll talk about in a few weeks. So what I could do is I could count up all the stars, dust, and gas in the galaxy using various types of telescopes, and I can estimate their mass. From the mass and centripetal force, I could figure out how much gravitational pull is on those, so how much centripetal force there should be, so how fast they should be going around. It's just a straight application of what we've been doing. Any star or planet or astronaut sitting out here is going to have a centripetal force and a velocity caused by that. So we do the comparison with what we observe, how fast it should be going versus how fast it is going, and what we find is that everything on the edge of the galaxy is going much, much slower than it should. So here's a plot to convince you. So here has got velocity versus the radius out from the center of our galaxy. What I expect is this dashed line here. I expect the stars to be going this fast. I expect them to be going slow. Now what's happening is they're actually going really, really, really fast. That's strange. It's almost as though there's a whole bunch of extra matter somewhere that's giving us extra gravitational attraction, that's giving us extra centripetal force that I can't see. This is our single biggest clue that the universe is made of mostly dark matter, and we have absolutely no idea what it is. All right, our last thought before we wrap this up. What about centrifugal force? Now, when I was in, say, high school, I heard people use words that sounded like centrifugal to me, and I kept wondering what centrifugal force was. Well, that's not a word. There's only centripetal and centrifugal. And I try to overemphasize the fuge in centrifugal. So what about this thing? This is a very real effect that really happens on rotating systems. Now, the reason that it exists is because these are non-inertial systems. So if I have an object on a merry-go-round, it keeps trying to obey the law of inertia. It keeps wanting to go in a straight line. However, from this rotating point of view, I need this extra force, apparently, from my perspective, that's going to make this thing want to go in a straight line. If I observe this from a stationary, non-rotating point of view, that is from an inertial frame of reference, objects go in straight lines and obey all the normal laws of physics. But because I'm rotating, what I see appears to be some kind of extra force. Now, if we think about centripetal force and Newton's third law, that is, I have this center-seeking force. Newton's third law says the equal and opposite is some outward pushing force. If the floor is accelerating against my feet put a force on the floor. And that lets me get far enough. There are some nice animations you can find online about why this works and how it works, but just know, centrifugal is a very real thing that happens because objects try to obey the law of inertia. They try to go in a straight line. If you've never heard of XKCD, you should probably pause this video now and go read a few hundred comics. They are the best that you can find in science. The only problem is some of them are wildly inappropriate to show in class. But you should go ahead and read this one about centripetal force versus centrifugal force. It's a very real thing that exists. So if I want to rotate, or I want to, say, facilitate childbirth by centrifugal force, it's real and it works. All right. In summary, circular motion at a constant speed is always accelerating. So that is, my velocity is always changing direction, which requires acceleration. To be always changing direction in a circle that is always turning, I need to have an inward force that is a centripetal force that causes a centripetal acceleration. I figured out that's going to be mv squared over r. Remember, there is not a new kind of force called a centripetal force. Any force that happens to point inwards can be centripetal. So we looked at examples of friction, the normal force, and gravity as being centripetal forces. Objects in orbit are in perpetual free fall with centripetal acceleration caused by gravity. All right, some really cool illustrations of a pretty simple concept of circular motion. We actually did rocket science today. It was a lot of fun. Thanks for watching.